You think you know reality, but your eyes betray you every day. Light does not travel in straight lines the way your brain tells you. Particles refuse to behave. Matter itself transforms into waves and back again while nobody watches. At the quantum level, interference patterns emerge that shatter everything you thought solid. 7 types of quantum interference exist right now, proving the universe operates on rules so alien they would make your ancestors call you insane. These are not theories. These are measured, documented, repeatable phenomena captured in laboratories across every continent, real particles doing impossible things. The double-slit experiment gets all the press, but that famous setup barely scratches the surface. Each interference type reveals different scars in the fabric of reality, and each one forces physicists to rewrite what seemed certain. Number 1. The original sin, Young's double-slit with single particles, not light beams, individual photons. One by one, this is where sanity first collapsed. In 1801, Thomas Young proved light behaves as a wave by sending beams through 2 narrow slits and watching interference fringes bloom on a screen. Bright bands where waves reinforce, dark bands where they cancel. Classical wave physics, nothing weird yet. Then quantum mechanics arrived and physicists started firing single photons. 1 photon enters the apparatus. 2 slits wait. Logic says the photon must pass through slit A or slit B. Pick one. Cannot be both. But the interference pattern still appears. Not immediately. Fire 1 photon and you get 1 dot on the detector screen. Fire 10 photons and you get 10 random dots. Fire 10,000 photons and suddenly those dots arrange themselves into the classic interference bands. Each single particle somehow interfered with itself. This should not be possible unless that particle existed in superposition, passing through both slits simultaneously. The photon becomes a probability wave that samples both paths, then collapses into a single detection point. The mathematics work perfectly. The conceptual horror remains unchanged. G. I. Taylor first demonstrated this in 1909, reducing light intensity until photon emission events barely overlapped. Individual clicks on the detector building toward the pattern. By 1974, Pier Giorgio Merli and colleagues in Italy fired single electrons through a biprism and watched interference accumulate 1 electron at a time. Published results showed the statistical buildup matching quantum predictions exactly. In 2002, Physics World readers voted the single electron double slit the most beautiful experiment in physics, edging past Galileo's falling bodies. By 1999, researchers at the University of Vienna pushed interference into massive molecules. Anton Zeilinger and Marcus Arndt fired buckyballs through gratings, C60 fullerenes, 720 atomic mass units, 60 carbon atoms locked in a soccer ball shape, 174 internal vibrational modes, hot molecules at 900 Kelvin radiating like classical thermal bodies, yet still producing interference fringes with wavelengths around 3 picometers. Published in Nature, October 1999. Each fullerene delocalized across neighboring slits, matter waves for molecules that should behave classically. The team later pushed to C70, then in 2011, Stefan Gerlich, working with Marcus Arndt, demonstrated interference with molecules reaching 6,910 atomic mass units and 430 atoms. Tetraphenylporphyrin derivatives with perfluoroalkyl chains, TPPF 152 unfolded to 60 angstroms, the largest molecules ever shown exhibiting quantum wave behavior, published in Nature Communications, April 2011. These were not atoms. These were molecular complexes with over 1,000 internal degrees of freedom, maintaining coherence long enough to diffract. If you value documented quantum mechanics and molecular interference like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual using sources from Nature Journal, October 1999, where Arndt, Nyers, and Zeilinger published wave-particle duality of C60 molecules, showing fullerene diffraction at nanomechanical gratings, and Nature Communications. April 2011, where Gerlich and colleagues published quantum interference of large organic molecules, demonstrating interference with molecules up to 6,910 AMU, proving quantum coherence in massive complex systems. Now back to the information. Number 2, the eraser that breaks causality, Wheeler's delayed choice quantum eraser. John Archibald Wheeler proposed this in 1978 as a thought experiment. Decades later, technology caught up. The setup uses entangled photon pairs generated through spontaneous parametric down conversion in a beta barium borate crystal. One photon called the signal heads toward a double slit, while its entangled twin, the idler, takes a different path with detectors arranged to either preserve or erase which path information. Here's where it gets strange. The signal photon hits the screen first, before any measurement occurs on the idler. No interference pattern appears in the raw data, just two overlapping Gaussian blobs. But after the idler photon gets measured and the data sorted by coincidence, detection, interference, fringes emerge in specific subsets. When idler photons land at detectors that erase which path data, the corresponding signal photons on the screen show interference. When idler photons hit detectors that preserve which path information, the corresponding signal photons show particle behavior. The measurement on the idler happens nanoseconds after the signal detection, but determines whether the signal photon displays wave or particle characteristics. It looks like the future rewrote the past. Yoon-Ho Kim and colleagues at University of Maryland, Baltimore County performed this experiment in 1999. Published results showed clear interference patterns appearing only in the erased datasets. The signal photon impacts the screen. 8 nanoseconds pass. The idler photon reaches its detector. Coincidence counting reveals the correlation. The mathematics show no actual retrocausality. The key insight involves quantum entanglement and correlation, not communication. Physicist Ruth Kastner argued in 2024 that the delayed quantum eraser resembles a standard EPR pair, where space-like separated operations commute. The order of measurements does not matter because both events occur outside each other's light cones. Published analysis in Quantum Studies, Mathematics and Foundations, March 2024 by Dix and colleagues showed step by step that delayed and non-delayed versions produce identical final quantum states. No retrocausation required. The wave function contains all information from the start. Measurement merely reveals correlations already present in the entangled state. Published in Nature Scientific Reports, January 2023 by Ham and colleagues demonstrating delayed choice quantum erasers using coherent photons showed the violation of cause-effect relations arises from selective measurement basis, choice, not temporal paradox. The data cannot be interpreted as the future changing the past, but the effect still demonstrates superposition and entanglement operating across space like intervals. Number 3, magnetic ghosts, the Aharonov-Bohm effect. Yakir Aharonov and David Bohm published their proposal in 1959 in Physical Review. They asked what happens when you split an electron beam so it travels on opposite sides of a solenoid containing magnetic flux, but with zero magnetic field in the region where electrons travel. Classical physics predicts nothing. No field, no force, no effect. Quantum mechanics predicts a measurable phase shift because the vector potential remains non-zero even where the magnetic field vanishes. The electrons never touch the magnetic field, yet their wave functions accumulate different phases proportional to the enclosed magnetic flux. When the beams recombine, interference, fringes shift, revealing the invisible influence. This was controversial for years. Critics argued electrons must be leaking into regions with actual fields. Robert Chambers reported the first experimental confirmation in 1960 using electron interferometry with a magnetic field from a thin iron whisker. Skeptics remained unconvinced. The breakthrough came in 1986 when Akira Tanomura at Hitachi published results in Physical Review Letters. His team used a toroidal magnet completely covered with superconducting material, preventing any field leakage into the electron paths. Perfect magnetic shielding. The interference pattern still shifted with the period depending on the magnetic flux, quantum h over e. The electrons detected the vector potential with zero magnetic field exposure. This result elevated the vector potential from mathematical tool to physical reality, or at least showed quantum particles respond to gauge potentials, not just forces. The phase shift equals e over h times the line integral of the vector potential around the closed path, which by Stokes' theorem equals the magnetic flux through the loop. Electrons going clockwise acquire phase e divided by h times phi. Electrons going counterclockwise acquire the opposite phase. The relative phase shift becomes 2 e phi over h, producing observable interference with period matching the flux quantum. Tanomura's paper showed diffraction patterns with flux increments revealing the quantized nature of the effect. This was not a small correction. The phase shifts reached multiple periods with strong visibility. Published results demonstrated that electromagnetic interactions in quantum mechanics fundamentally involve potentials, not just field strengths. Nobel laureate Chen-Ning Yang and physicist Tai-Tsun Wu showed in 1975 that the Aharonov-Bohm effect connects to gauge theory and topology, revealing deep structure in quantum electrodynamics. More recent work in 2014 by Lee and colleagues demonstrated a photonic Aharonov-Bohm effect using non-reciprocal phases in acousto-optic crystals, published in Nature Communications, showing the phenomenon extends beyond charged particles. In 2022, Christian Rouse and colleagues reported a gravitational Aharonov-Bohm effect using atom interferometry, published in Science, demonstrating gravitational potentials create measurable phase shifts analogous to electromagnetic ones. These experiments prove quantum interference responds to gauge structure, not merely forces. Number 4. 2. Photon magic, the Hong-O-Mandel effect. Chunki Hongjae Aos and Leonard Mandel performed the experiment at University of Rochester in 1987, published in Physical Review, Letters, November 1987. The setup looks deceptively simple. 2 identical photons approach a 50-50 beam splitter, 1 photon entering each input port. Classical intuition says each photon has 50% chance of reflection and 50% chance of transmission. So you expect 4 possible outcomes. Both photons reflected, both transmitted, 1 reflected, 1 transmitted, 1 transmitted, 1 reflected. 2 of those outcomes put photons in different output ports, triggering coincidence detection. Quantum mechanics predicts something else. When the photons arrive simultaneously and are indistinguishable in all properties, polarization, frequency, spatial mode, the probability, amplitudes for the 2 paths where photons exit separately interfere destructively, perfect cancellation, 0 coincidence counts. Both photons always exit together in the same output port. 50-50 chance of exiting in output A together, 50-50 chance of exiting in output B together, 0 chance of exiting separately. Hong, Ao, and Mandel verified this by varying the arrival time difference, scanning a delay line. When photons arrive, perfectly synchronized, coincidence counts drop to 0, a dip in the coincidence rate, the Hong-Ou-Mandel dip. The width of the dip measures the photon coherence time. The visibility of the dip quantifies indistinguishability. They achieved deep dips with thermal light in 1987 then, with single photons from parametric down conversion. Since then, the effect has been demonstrated with atoms. In 2015, Raphael Lopes and colleagues at Institut d'Optique reported atomic Hong-O-Mandel interference using metastable helium atoms, published in Nature, April 2015. 2 atoms entering a beam splitter analog showed bunching behavior analogous to photons. The effect extends beyond photons to any bosonic particles. In 2024, Max Ehrhart and Andreas Samait published topological Hong-O-Mandel interference in Science, June 2024. They showed interference determined solely by synthetic magnetic flux, rendering it resilient to errors at a fundamental level. The quantum superposition accumulates measurable phase shifts depending on photon properties in optical cavities. Their implementation established quantized flux, facilitating exclusively destructive quantum interference, opening pathways toward topologically protected quantum gates. The Hong-O-Mandel effect serves as foundation for linear optical quantum computing. Every CNOT gate implementation for photonic qubits relies on this 2-photon interference. It proves photons do not merely act as independent classical particles, but exhibit quantum statistics requiring amplitude-based calculations. The coincidence probability goes as the square of the sum of amplitudes, not the sum of individual probabilities. Published experiments show visibilities exceeding 70% and approaching 90% with optimized sources demonstrating genuine quantum behavior far beyond any classical threshold, which sits at 50%. If you value documented quantum optics and 2-photon interference like this, subscribe. It is the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual using sources from Physical Review Letters, November 1987, where Hong-O and Mandel published measurement of sub-picosecond time intervals between 2 photons, by interference establishing the canonical 2-photon interference effect in Science. June 2024, where Ehrhart and Samait published topological Hong-O-Mandel interference, demonstrating interference controlled by synthetic magnetic flux with resilience to fundamental errors, proving topology protects quantum gates. Now back to the information. Number 5, the atomic clock inside a wave, Ramsey interference. Norman Ramsey developed this in 1949, building on ideas from his mentor Isidore Rabi, who pioneered magnetic resonance methods for measuring particle transition frequencies. Ramsey's innovation split the interaction into 2 separated oscillating fields. An atom in its ground state enters the first interaction zone, where a microwave or optical pulse creates a coherent superposition of ground and excited states. A 50% probability for each. Then the atom flies through a field-free region, maintaining the superposition while accumulating phase. Then a second pulse in the second interaction zone mixes the states again. If the laser frequency matches the atomic transition and the two pulses maintain proper phase relationship, the atom ends up fully in the excited state. If the phase drifts, the atom ends partially in ground, partially in excited states. By scanning the microwave frequency and monitoring the excited state population, you see Ramsey fringes, oscillations as a function of detuning with narrowness determined by the time between pulses, not the duration of the pulses themselves. This separates the interrogation time from the interaction time, enabling much higher resolution spectroscopy. Every atomic clock uses this method. Cesium fountain clocks, NIST F1 and F2 in Boulder, Colorado. Laser-cooled cesium atoms launched upward pass through the first microwave cavity, then coast through free flight for about 1 second, accumulating phase, then pass through the second cavity. The Ramsey fringes have line widths below 1 Hz for transition frequencies near 9 GHz. Fractional frequency uncertainties reach parts in 10 to the 16th. These clocks define the second in the International System of Units. The definition reads, the second is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of cesium-133. That number comes from Ramsey interferometry. Published results from NIST show systematic uncertainties below 1 part in 10 to the 15th, with years of operation proving reproducibility. Optical atomic clocks using strontium or ytterbium now push toward 10 to the 18th fractional accuracy. These systems use Ramsey sequences with optical frequencies around 500 terahertz. The interrogation times reach seconds. Single-ion clocks and optical lattice clocks both implement Ramsey methods. Klaus Milmer and colleagues demonstrated in 2018 that Ramsey interferometry with trapped motional quantum states in optical lattices enables studies of quantum, many body dynamics published in Nature Communications, June 2018. More recent work in 2024 by Gysi and colleagues used Ramsey clocks to measure tunneling times, showing how atoms in coherent superpositions of internal states reveal interaction times with quantum barriers, published in Science Advances, May 2024. The phase accumulated during tunneling provides operational definition of elapsed time without invoking classical trajectories. Ramsey interferometry appears everywhere. Maser and laser technology, quantum logic gates, trapped ion qubits, superconducting qubit readout. Anywhere precise control and measurement of quantum superpositions matters. You find Ramsey sequences. The method exploits quantum interference between states evolving at slightly different frequencies. The contrast of the fringes measures decoherence. The shift of the fringes measures external perturbations, magnetic fields, electric fields, gravitational potentials. Any influence that couples to the atomic transition shows up as a phase shift in the Ramsey pattern. This makes it the workhorse for precision measurement. Atomic magnetometers use Ramsey sequences to detect magnetic field changes at femtotesla sensitivity. Gravity gradiometers use atom interferometry with Ramsey-type configurations to map underground density variations. Every application relies on the fundamental quantum interference between coherently prepared atomic states. Number 6, molecular monsters doing the impossible, matter wave interference of complex molecules. When particles get bigger, quantum effects should disappear. Decoherence from environmental interactions destroys superposition. This is why chairs and cats do not diffract, but the boundary keeps moving. We already mentioned buckyballs in number 1, but the story goes further. Stefan Gerlich, working with Marcus Arndt, pushed to perfluoroalkylated nanospheres, PFNS8 with mass 5,672 AMU. C60 with 12 fluorine chains attached, PFNS10 with mass 6,910 AMU and 430 atoms. Published Nature Communications, April of 2011. These molecules had over 1,000 internal degrees of freedom, rotations, vibrations. They should couple strongly to their environment. Blackbody radiation, collisions with residual gas, internal thermal noise. Yet the Talbot-Lau interferometer showed clear fringes. Interference contrast exceeded 50% visibility, meaning quantum coherence survived. The de Broglie wavelengths reached 1 picometer, smaller than an atomic nucleus. The molecules traveled at 100 meters per second. The gratings had 100 nanometer periods, each molecule delocalized across multiple grating slits simultaneously. Published measurements showed the interference pattern shifting with applied electric fields, confirming genuine matter wave behavior, not artifacts. Then came biological molecules. In 2020, Yakov Fein and colleagues at University of Vienna demonstrated matter wave interference with gramicidin, published in Nature Communications, March 2020. Gramicidin A is a natural antibiotic. a polypeptide of 15 amino acids, mass 1,882 AMU. This was a biomolecule, not a synthetic cage designed for stability, an actual protein fragment that exists in living systems. The Talbot-Lowe interferometer used 3 optical gratings with laser light creating standing wave patterns. The molecules passed through, heated by laser pulses for desorption, then carried in an argon stream at 600 meters per second. Detection via laser ionization. The center of mass wave function delocalized over distances 20 times larger than the molecular size. Interference fringes appeared, matching quantum predictions. The experiment proved quantum behavior extends to complex biological macromolecules under appropriate isolation from decoherence. Published analysis showed the coherence depended critically on minimizing photon scattering during flight. Each scattered photon carries which path information collapsing the superposition. The molecules had to remain dark, passing between the gratings without absorption or emission events. This required careful wavelength selection and low photon flux. The result demonstrated that life's building blocks obey quantum mechanics when environmental coupling gets suppressed. Not relevant for biological function, where environments couple strongly, but proving the universality of quantum theory up to nearly 2,000 atomic mass units. These experiments address fundamental questions. Where does the quantum to classical transition occur? Can macroscopic objects exhibit superposition? What role does measurement and environment play in collapse? The current record stands at around 7,000 AMU, but proposals exist for nanoparticles reaching millions of AMU. Optomechanical systems trap silica spheres of 10 to the 14 AMU in optical cavities, attempting to prepare them in quantum ground states. If successful, these would represent the most massive objects ever in quantum superposition. Matter wave interferometry provides direct tests. Future experiments aim for proteins, DNA fragments, even viruses. Each step larger tests the boundaries of quantum mechanics versus classical emergence. Number 7. The oscillating ghosts of excited states. Quantum beats. When you excite an atom with a short laser pulse broad enough in frequency to span multiple energy levels, you create a coherent superposition of excited states. These states have different energies, so they evolve at different rates. The atom's fluorescence oscillates in time as the states acquire relative phases, then realign, then shift apart again. These oscillations, quantum beats, arise from interference between decay amplitudes, from the different excited levels to common ground states. They were first observed in 1955 by Forrester, Goodmanson, and Johnson, mixing Zeeman components in a magnetic field. Since lasers arrived, quantum beats became standard tools in atomic and molecular spectroscopy. Here is the mechanism. A short pulse at time zero creates a superposition. The excited state wave function equals a linear combination of sublevels, each with its own energy. As time passes, each sublevel accumulates phase at a rate proportional to its energy. The relative phases between sublevels oscillate. When the atom decays back to the ground state, the fluorescence amplitude equals the sum of contributions from each sublevel. These contributions interfere, constructively when phases align, destructively when phases oppose. The fluorescence intensity shows temporal modulations at frequencies matching the energy differences between excited sublevels divided by Planck's constant. Measuring these beat frequencies gives precise values for energy splittings. Hyperfine structure, fine structure, Zeeman splittings, Stark splittings, any level structure within the excitation bandwidth produces beats. Published experiments demonstrate quantum beats in rubidium vapor. Exciting the D1 or D2 lines with femtosecond pulses creates superpositions of hyperfine levels. The resulting fluorescence shows oscillations at megahertz to gigahertz frequencies, depending on which transitions are involved. Time-resolved detection with fast photodiodes or streak cameras captures the dynamics. Fourier analysis extracts the beat frequencies with precision limited by coherence times. Typical measurements resolve splittings to kilohertz accuracy. In 2025, researchers published advanced undergraduate labs implementing quantum beat spectroscopy in rubidium using distributed feedback lasers and simple photodiode detection, published in American Journal of Physics, February 2025. Students observed beat frequencies around 3 GHz, corresponding to hyperfine splittings in the 5p3 halves excited state. The experiment demonstrates quantum coherence and interference in atomic systems directly accessible to undergraduates with modern equipment. Quantum beats extend beyond atoms. Molecules show beats from rotational levels, vibrational levels, electronic states. Solid state systems exhibit beats from excite and fine structure. In 2018, researchers demonstrated an ultra-fast quantum beats in atomically thin rhenium disulfide, showing coherent superposition of anisotropic excitons with different orientations, published in Nature Communications, March 2018. The beat frequency matched the energy splitting between the two excitant states, enabling characterization of electronic structure in two-dimensional materials. Semiconductor quantum dots show quantum beats, revealing fine structure and hyperfine coupling. These measurements inform the design of quantum dot qubits for quantum information processing. Every case involves the same physics. Coherent superposition of states with different energies, interference between decay or scattering amplitudes, temporal oscillations. Encoding energy differences, quantum beats provide Doppler-free spectroscopy. The beats occur in the time domain independent of atomic velocity. This eliminates Doppler broadening that plagues frequency domain measurements in room temperature vapors. The method works for short-lived states inaccessible to continuous wave spectroscopy. As long as the coherence survives longer than the inverse of the energy-splitting beats appear. This typically requires picosecond to nanosecond coherence times depending on the system. Modern ultra-fast lasers enable measurements on femtosecond timescales, resolving beats from electronic states separated by electron volts. So there you have 7 types of quantum interference. Proving reality operates on rules that defy human intuition. Single particles interfering with themselves through double slits. Delayed choice erasers showing entanglement across space like intervals. Aharonov-Bohm phases from gauge potentials with 0 field strength. Hong-O-Mandel 2 photon bunching from indistinguishable bosons. Ramsey fringes defining time itself in atomic clocks. Matter waves from molecules with thousands of atoms. Quantum beats revealing excited state structure through temporal interference, each one confirmed in laboratories. Each one published in peer-reviewed journals, each one reproducible. The double slit showed particles as waves. The quantum eraser showed measurement correlations transcending time ordering. The Aharonov-Bohm effect showed potentials, not fields, coupled to wave functions. Hong-O-Mandel showed photons obey quantum statistics, not classical probability. Ramsey interferometry became the foundation of precision timekeeping. Molecular matter waves pushed quantum mechanics into the mesoscopic realm. Quantum beats turned temporal oscillations into precision spectroscopy tools. These are not philosophy. These are engineering tools. GPS satellites use atomic clocks built on Ramsey interference to synchronize timing across the constellation. Quantum cryptography. Protocols use Hong-O-Mandel interference to verify photon indistinguishability. Electron microscopy uses Aharonov-Bohm phases to map magnetic fields at nanometer resolution. Spectroscopists use quantum beats to measure atomic structure. The effects discovered in fundamental physics laboratories become technologies deployed globally. Quantum interference underpins quantum computing. Every qubit, whether superconducting, photonic, atomic, or solid state, relies on maintaining coherent superpositions and exploiting interference effects for gate operations. Error correction schemes use interference to detect and suppress noise. Quantum algorithms from Shor factoring to Grover search exploit interference to amplify correct answers and suppress wrong ones. The entire field rests on these 7 types and their variations, but mysteries remain. Why does measurement collapse superposition? The double slit interference vanishes when you detect which slit the particle traversed. Place a detector at slit A or slit B and the pattern disappears, replaced by 2 simple distributions. The detector entangles with the particle, introducing witch path information that destroys interference. But what constitutes a measurement? Does it require a conscious observer? Does it require irreversible amplification? Does it require environmental decoherence? Decades of debate and experiment have not settled the question. Decoherence theory explains how interactions with large environments suppress interference in practice, but does not resolve the interpretation of quantum mechanics itself. Many worlds interprets all outcomes as real in branching universes. Copenhagen treats measurement as fundamental and irreducible. Bohm mechanics adds hidden variables and non-local dynamics. Cubism treats quantum states as personal information updated by experience. Each interpretation accommodates the 7 interference types, but assigns them different meanings. The quantum to classical boundary puzzles physicists. At what mass or complexity do objects transition from quantum to classical behavior? Buckyballs show interference. Grammacidin shows interference. Larger molecules may show interference, but cats do not. Somewhere between a polypeptide and a cat, the superposition collapses effectively, if not fundamentally. Decoherence predicts this transition based on environmental coupling. Molecules in ultra-high vacuum maintain coherence. Molecules in air couple. To photons and gas collisions, losing coherence on picosecond timescales. Place a fullerene in a thermal radiation field at 300 Kelvin and emission absorption interactions destroy spatial coherence within femtoseconds for separations exceeding nanometers. Yet, isolated properly, even massive molecules remain quantum. The question is whether this scales indefinitely, or whether new physics emerges at macroscopic scales. Gravitationally induced decoherence proposals suggest quantum superpositions of different mass distributions decay spontaneously from gravitational effects. Testing requires matter wave interferometry with nanoparticles, masses exceeding 10 to the 9 AMU. Experiments are underway. Results may reveal whether quantum mechanics remains valid at all scales or whether modifications appear. Entanglement propagates correlations across arbitrary distances instantaneously within the constraints of no faster than light communication. Einstein called it spooky action at a distance. Bell's theorem proved no local hidden variable. Theory reproduces quantum predictions. Experiments confirm violations of Bell inequalities with photons atoms superconducting qubits across kilometers of separation. The Hong-O-Mandel effect for entangled photons shows correlations persisting despite spatial separation. The delayed choice eraser shows correlations apparently transcending temporal ordering, though careful analysis reveals no causality violation. These phenomena demonstrate non-locality built into quantum mechanics. The wave function assigns amplitudes jointly to systems regardless of distance. Measurement outcomes correlate obeying joint probabilities that cannot factor into independent local terms. This is not communication. Information cannot be transmitted faster than light using entanglement alone, but it is correlation stronger than anything classical physics allows. Quantum interference enables and reveals this entanglement. Without interference effects, we would not have evidence for entanglement. The Hong-O-Mandel dip proves photons bunched. Two-photon interference in the delayed eraser proves entanglement across the signal and idler. Ramsey fringes and distributed atomic clocks probe entanglement between remote atoms. Molecular interference provides platforms for testing entanglement with massive particles. Now, here's the final measurement. The data that reframes everything. In 2022, a team at the University of Science and Technology of China achieved quantum interference with over 10,000 atoms simultaneously, not single particles diffracting one at a time. Massive ensembles maintaining coherence as a collective quantum state. They used a Bose-Einstein condensate, a cloud of rubidium atoms cooled to nanokelvin temperatures, where all atoms occupy the same quantum ground state. They split the condensate using optical lattices, creating a spatial superposition of the entire cloud. Then they recombined the paths and observed interference fringes in the atomic density distribution. Published results showed visibility approaching 90%, proving quantum coherence persisted across macroscopic numbers of particles acting collectively. This moves quantum interference from individual particles to many body systems. It suggests quantum effects may be scalable to even larger assemblies if decoherence can be controlled. It provides platforms for quantum simulation of condensed matter models. It enables precision sensing with enhanced sensitivity from entanglement between atoms, and it poses a challenge. If 10,000 atoms can be placed in superposition, where's the limit? Can a million atoms exhibit quantum interference? Can you interfere clouds massive enough to see with the naked eye? Well, the mathematics says yes, if isolation is perfect. The experiments say maybe if technology advances. The implications terrify and excite. Quantum mechanics might have no upper bound. Reality might remain probabilistic and non-local all the way up. Your chair might be a superposition that merely looks classical because decoherence happens faster than you can detect it. The universe might branch at every quantum event, creating worlds where every outcome occurs. Or the interpretation might be something else entirely, something nobody has imagined yet. These 7 types of quantum interference guarantee only one thing. Reality is not what it seems. The patterns prove it. The data are unambiguous. Welcome to the real universe. It runs on interference.